And today's topic is actually graph theory. And I made this into, oh, sorry. What did I do? Okay. I made this into two parts. So this part, you guys are, you guys have the same contents with the elementary division. And so we're going to start with graph theory and what the elementary school level would also do. So what is a graph? The graph is basically something like this. Okay? It has nodes, or we call it vertex, right? Vertices, A, B, C, and D in this simple graph, and edges that connect nodes. Okay? And a graph is made of these two sets of things, right? And with undirected graphs, that's what these are. And there's no direction on the edges. Basically, when we talk about direction, it's going from one node to another, right? And so this connection between A and B means A can reach B and B can reach A on the same connection. And this is a formula that says the number of edges in this graph would equals to vertices and diagonals. That makes a complete graph when that happens. All right. A complete graph is, however many nodes you have in this graph, you have one direct connection goes from every node to every other node in this graph. Say like this one, that we have 5 nodes here, right? There's a connection between AB, AC, AD, and AE, right? From each node in this graph to every single other node in this graph. And if you have a graph with more nodes in there, the same definition applies, right? If you have a direct connection between every node to other node in the graph, that would make it a complete graph. Okay, we're good. A path is like the path, right? Like we walk. Basically, if you have a way to reach from one node to another, that means there's a path, right, from A to B or A to C. So in here, in this graph, right, A to B, A to C, A to B, there's a graph, there's a path for you to do that. And we call the length of the path the number of edges between one, on that path from one node to the other, right? So from A to B, A to C, the length is 1. And from A to D, the length is at least 2, right? So you got to go from A, C, and D, or 3, A, B, C, and then D, right? It's, or if you want to go, a couple of circles here, you can do that too. Those are all paths from one node to another. In a complete graph, right, the shortest path from one node to another to any other is 1, right? And then there's the concept of connected graph. The connected graph means that from every node you have a path to go to another node. any other node. Right? And this one is a disconnected graph, right? Because there's no way to go from A to C here or B to C. Right? Yeah. Okay. So for this one, if we say from B to D, right, from B to D, do we have path of length 3? For example, BAED, that's 3, right? There are 3 edges in this path. And there are others too, right? BCAD, that would be the path of 3 as well, right? And BCED, that would be 3. Why do we talk about these things? We'll get to that later. But what I can tell you is that all these theories, these kind of, a lot of these things look very easy, right? You can eyeball them on here, on this screen. But think about the internet. The internet basically is a big graph, right? You got all these computers on the internet, right? And you want to be able to reach from one computer to any other computer on the internet, right? That's what internet is. That is basically what this is, right? It's just more complicated. So yeah, there you have connected and disconnected graphs. So this is another problem called traversability, and this was a kind of a famous old story from old Europe. And you have this town, the city called Königsberg. It's Persian and I guess sort of pronounced like as in German, I guess. So you have the town. It's on the 2 sides of a river, right? The town goes across the river. That you got a lot of those in Europe. And there are 2 islands inside in the middle of the river. And then you got the bridges connecting all these places, right? Because I guess this sea probably should be a bigger island because you got 5 bridges going in and out of that island, right? And then, so there are all 7 bridges connecting the islands and the islands to the riverbanks, right? So you got all parts of the city connected. I guess today I don't know how many bridges are like around New York. It's similar, right? You got New York has 3, what do they call it, bergs. So you got 3 major parts, right? And then there are bridges connecting those parts. And the traversability issue is, if you can you actually go walk across every single bridge once and only once, and then you walk through all of them, but you can't go backwards, right? So let's say if you walk from A to C on this P bridge, you got to walk over, and then once you're on C, you got to walk over another bridge to reach another part of the town. So the problem is, if you could if you could actually walk all the bridges without walking on any one of them twice. Right? Can you think you can do that here? Yeah. And right, you cannot jump into the river. You cannot jump over the bridge and things like that. So what actually Euler is a famous mathematician back then, right? So what he did is basically converting that picture of the town, the map of the town, into a graph like this, right? So if you don't look at that as a huge mass of land, but look at it as a node, right, on the graph. Yeah. So this is the same map as we have on the next page, right? It's okay.
Yeah, well, I feel I feel very
Okay. So the question is, can you do that or not? Right? I mean, and also, this is also a generic question, right? Can you do that in this map on in this town, right? If you can, what about another town with another setting, right? So, and what he discovered is that if you convert this into a graph like this, so it would basically be A, B, C, and D. And then with these edges connecting them, right? It would be the same thing. And then we introduce a concept called the degree of the vertex. So the A node has 3 degrees, meaning that it has 3 connections going in and out of this place, right? Remember, this is undirectional, so you can go either way. You can walk from A to C and then also C to A. But this particular question is asking you if you could, traverse all of them without walking on any bridge or any of these edges twice. Right? So so what Euler discovered is that for a graph to be traversable, it can only have 2 or none of these nodes with odd number of degrees. Okay, so for example, in this one, we can count, right? It's easy to count. A has a degree of 3, right? And D is 3, B is 3, and C is 5. So we have 4 nodes here, and all of them have odd number of connections. So that basically says this graph is not traversable, meaning that you have to walk on one of the bridges at least more than once. Right? So this is a problem with an interesting problem with dealing with traversing a graph. Right, any questions about these? Yep. Right. So any kind of graph you have. Let's go back to a simpler one like this, right? This one, we count all 4 nodes. And you got A and B that has 3 connections out, right? So this one is possible to traverse. But now if you add a connection from C to D, then it becomes not possible. Right? That makes sense? And so you can, this simple graph, you could probably kind of eyeball it. You can go A, B, C, and back A, and then D, right? And then, yeah. So you walk on the edges, all of them, and every single one of them once. So that's the part that we're sharing with all divisions. Right. So here's a different set of problems. Right. Again, graphs. We got these definitions, and then a different way of defining a graph is using these 2 sets. Right, a set of vertices, right, all the nodes in this graph, and then a set of edges, a set of connections in this graph. Right, in this, you got AB, AC, AD, and then BC and BD, right, because these are non-directional. You can do that. And then for a directed graph means that you got a direction associated with each edge, right? So in this case, from A to B, it's directional. You can only go from A to B, not B to A, right? That's what this means. And again, we can use the same description to present this graph. Yeah. This one. You don't have to, this should be intuitive, right, on this one. And you got a set of nodes, and you got a set of edges. With directed graph, these AB means the direction of that connection from A to B, right? And then from A to D, you have A to D, and then there's also D to A, right? So basically, the bidirectional edges basically mean that there are 2 connections in a directed graph, right? Making it 2 edges essentially. So if you think of undirected graph in a different way, you could think of them as directed graph with all edges that are bidirectional. Right? Yeah.
Does that mean they can cross the rule of bidirectional edge line?
No. It still doesn't mean that. Right. You can think, I mean, if you have a bidirectional, if you're talking about undirectional graph, right, and you're talking about 2 edges between each node, but they are directional, right? So if you treat it that way, then let's say from A to B, you can walk. If this is a bridge, and that means you can walk from this side to the other side, but you cannot come back, right, on the same bridge. And also, you've got this concept. I don't know if that doesn't. I don't know if that's important concept, but in this whole graph, actually, there is no cycle, right? You cannot, because you, for example, you walk from H to G, and then you come back to E, but this edge is in the other direction, right? So there's no way to go in circle in this one. Rather, and then if you look at this, because this is undirected graph, or if you want to make them all, bidirectional connections, right? Then that means you have a connection that goes this way, and then a connection goes this way, and then go back here. So that makes a cycle, right? You can come back to the point where you started your path. Okay. And so another concept is trees, right? Did we talk about trees in another session, right? A tree is in the graph theory is a graph with no, or I should say a undirected graph, right? With no cycle. So there's no way to create a cycle in any part of this graph. Then it is basically a tree. You can basically pick up any node and pull it out, and it becomes, take that with using that node as the root, right? It becomes a tree. A tree with n vertices contains exactly n minus 1 edges. So for example, this one has 4 nodes, right? You got 3 edges, 3 connections in there. You add one more, it's not a tree anymore, right? You add anywhere you add one more edge, you create a cycle, create a circle, and then it's no longer a tree, right? So if you have this, if you look at this whole thing as a graph, and you have multiple trees in there that are disconnected, right? That they're not connected in any way between them, then this is called a forest. I guess it's similar to what we have in nature as forests, right? And then you can also have weighted graph. If you add weight, add a associated or added a value, right, associated with each edge. If you do that, then that becomes a weighted graph. And also a spanning tree, sorry. A spanning tree is a graph, right? If you have a graph, and then if you have all the vertices in that tree, right, that becomes a spanning tree. And a minimal spanning tree can be found for weighted graph. If it's not weighted, then any spanning tree is essentially a minimal tree. Right? But with a weighted graph, meaning if the edges have different values on them, then it is possible for you to find a minimal spanning tree. Again, why are these concepts important? Right? I would like to go back to the internet again. If you ever have a chance to go into, networking, These are the theories that basically runs the internet. Okay, on the internet, as we say, a computer here, like my laptop, can reach any computer anywhere on the internet, right? As long as they have a public IP address. So if I go to Google, right? Google in their data centers have thousands of computers actually, right? Thousands of servers running different stuff. And if I go to Google and type www.google.com, I can actually reach any one of them that is running that domain name, right? That is running a web server, a web service for that domain name. How do I do that, right? I'm not a magician. I don't have anything that's magic on this computer. What this computer does is this computer actually doesn't have much knowledge of the network at all. But what this computer has is it knows a default route, right? A default route meaning that this computer only has one connection going out to the internet, right? Which is through the Wi-Fi card on this computer to that router in the back room here, right? That's the default route, what we call it. I know how to get to that, right? Because I have a Wi-Fi connection to it. And if that router has like 5 computers connected, like right now, right? If you have a few computers here on these tables, we can actually talk to each other. This computer can talk to each other, right? How do they do that? It's because when we connect to that router basically builds a graph in its memory, right? So the router knows how many nodes that are currently connected to it, right? The router is a box, and we are connecting to it with Wi-Fi connections, through Wi-Fi connections, and then let's say the Chinese school can also have a computer, say, connected to that router, which then could allow us to, talk to that computer. And then how does that router know how to reach to Google, right? It doesn't have that knowledge either. But then again, it has a default route to the service provider, right? Which is probably Comcast in this case, right? It has a connection going out to Comcast somewhere. And then on the Comcast network, they have bigger routers, right? That has, that connects all these customers, right, to the Comcast network. And that Comcast router knows how to get to its customers, right? Because you guys connect to it. And then it also knows how to reach other networks. Not all the other networks, okay? There are millions of other networks on the internet, right? It only knows a few of them, right? That's what the internet looks like to each one of these routers. Okay, a node is just, for example, this node only has knowledge of what is connected to it, right? But then it knows how to reach another level of service provider that has more other networks connected to them. Right? Comcast, again, in turn, is connected to some other network. That's how the whole internet is built. Okay, so each node doesn't know how to, get to this one, for example, directly, right? It has no knowledge even that one existed, right? But when I looked up www.google.com, it gave me an IP address, right? A number, And I put that number in my packet that goes out from my computer, goes out to this router. And this router goes out to another router and goes over to another router. And then eventually that packet gets routed to the destination. Right? That's how the internet works. And that's how actually, the graph theory, spanning tree, and all that stuff. These theories are used in those routers when they, built these connection tables, right? Because on the internet, anything can happen anytime, right? Let's say if something happens to this building, right? And the router in here goes down, and then we lose connection to the internet, right? But for a service provider, when they provide this kind of service, they're not going to have just one router, right? They have redundancies, right? So what they have is actually something more like this, right? Or even more complicated for let's say A, B, C, D, E. These are service providers, right? They are more likely to interconnect with each other, right? Having multiple connections to other parts of the network. And the graph theory is how, that type of connection gets reduced into spanning trees, right? Because if you have cycles, then that means your packets can go round and round in that network, right? When it does that, it may not be able to reach the destination at all, right? When it goes round and round in the network. So these are why we're studying the graph theory and why they're important. Yeah.
I still don't understand about the spanning tree. Can you help
Let's say this is a graph, right?
Yeah.
But it's not a tree, right? A tree means that you can't have cycles, you can't have circles, you can't run circles in that graph, right? That kind of graph is a tree. So if you have a graph and then you take some edges out of it, and then it becomes a tree, meaning that there's no cycle in there anymore. But you still have all the nodes connected in that graph, in that tree, right? That means that tree is a spanning tree for this graph. That means because you can still get to all the nodes in this graph. That's what it means. From any one node to any other node. That's what spanning means, actually. And actually, spanning tree are for the most part it is dynamically built, meaning that, let's say, when you have a router, right? If A is a router, B is a router, they're all interconnected with each other, like in this case. You don't want to, for example, A knows how to get to B, right? But it doesn't know how to, it also knows how to get to C, for example, right? And so, so if A wants to send a packet to anybody, the A could just send that directly, right? But if A has a packet that is they're broadcasting packets, right? Meaning that sometimes A needs to send this thing out to everybody that it connects, right? It sent out to everyone in this network, and then let's say B gets that, And then it also wants to broadcast that, right? Let's say B does not, not only has connections to these guys in the network, it also has things on the backside, right? So now if you receive something from A, and you would have to know that from your spanning tree, you have, connections to, A has connections to all these other nodes that you directly connect to, right? So you don't want to broadcast that to everybody, no. Right? Because if you do that, then that means E will get this packet multiple times, which is not only a waste of resource, but also it creates trouble in the network, right? Because every single connection here has a limited capacity. That's what that weighted graph come in, right? Because you have to know how much you can send on a particular connection if you're building a network, right? So these, let's say if this is a router, right? It has connections to the outside, and let's say if it's a full graph, then you have these connections too, right? And that not all of these connections are running at the same speed, right, on the internet again. So you have some, let's say some of these connections are fiber networks, optical fibers. They run, hundreds of gigabits per second. And then on some other connections, you don't have that kind of speed. So you have to weigh how much data you can send on these connections, right? So that's where all these concepts come in when you, work with that type of connections, right? A network is basically a graph. Okay, so a minimal spanning tree then becomes important, right, for a weighted graph when you have a internet type of network, right? So let's say if you have, let's say if this is actually a full graph, right? And with all these connections, these three that are much higher speed than others, right? Then when you build your spanning tree, you want to use these higher speed connections first, right? Because they can sustain more traffic than others, right? That makes your whole network run better, right? So that's why you need these concepts. You need to build these kind of trees and like building a minimal spanning tree from a graph, right? And this is another way of mathematically presenting a graph. Right? This is a directional graph. Okay, every connection has directions, right? When we use this adjacency matrix like this, right? This means we have a connection from A to B, right? From A to B, and then from A to D, right? And nothing else. So if we have a 1 in this spot, that means there's a connection that goes that way it goes that direction, right? Like from here, you have one from B to C, and then there's also from C to B. So there you have a byte. Well, this is written or drawn in two directed connections, right? But you can also do just a bidirectional connection. That's what this adjacency matrix means, right? And so and then you fill up all the other spots that has no connection with 0. This makes up the a matrix, right? And if you want to figure out if there are paths of length 2 from one node to another, you can simply do a multiplication of these two matrices. Okay, for example, if we did that, right? We did m times m, and we got to this, and we have AC. This spot has a 2 in it. What does that mean? Right, that means we have two paths of length 2, right? Because this is m to the power of 2, right? M times m from A to C, from node A to node C. And as we can see, eyeballing, right, from this one, we can go from A to B to C, right? A to B to C. Or we can go from A to D to C, A to D, and then to C. Are there any other path of 2 between A and C? There's not, right? So this is a mathematical formula for you to figure out if there's a way, right, for you to go from one node to another, right? And also you can figure out what is the shortest path to get there, right? This is a simple graph, so we can really kind of just eyeball it, right? So let's say from A to D, it's just 1, right? Direct connections from this matrix. And let's say if you want to go from D to A, right? You know that there's no direct connection, and that there's also no connection, no path of length of 2, right? There's just seems to be no way to get to A from D, right? So this basically gives you a way of, building that, shortest, the minimal spanning tree and all that stuff. You can basically figure things out from doing simple math on the matrix, right? And then in general, this is basically the rule, right? If you do this multiplication multiple times, and then you can figure out if there's a path of length p from any node to any other node, right? So if you do this multiple times, and then if there's a 0 in that spot, then there's no path of that length from that node, from in here, which is from C to, let's say, B. Right? There's no path of length 2 to get there. But from this one, you can see that there's a direct connection from C to B, right? Any question about that? So this is how you can figure out, right, if you have connections, and then if there's, what is the shortest path, right, from one node to another. So if this network becomes, or this graph becomes complex, you have more nodes in it and more interconnections, but it's hard to figure out. And again, going back to internet, for example, let's say even if all these connections are bidirectional, for example, you can have a cable cut, right? A fiber cut, meaning that, when we have a lot of fibers going from, let's say, from Detroit to Chicago, and then going out to the internet. And somebody runs a backhaul somewhere in between, right? I don't know, somewhere along I-94, for example, and digging into the ground and cut the fiber. Those kind of accidents happen in the past, right? So if you have somebody cutting this connection for you, then these routers would have to figure out, because it can figure out, well, I lost my connection to that guy, right? And now I got to figure out if I still have a way to reach out to the internet, right? Because things like that happen dynamically, and these routers, these devices will have to have ways, algorithms, right, to figure out things dynamically also. So when let's say A loses the connection to B, it will have to figure out, okay, now what do I do, right? Now if I need to send something over to B, what do I do? Do I still have a connection? And if this is a, you know, if we look at all these connections as bidirectional, then you would have another way to reach B, right? That's how, you know, the whole internet thing works. So here's a problem. Let's take a break and then we can do these problems. Okay, so yeah, I kind of assume that everyone knows how to do multiplication of matrices. No? Okay. So matrix multiplication. Oh, let me go grab it.
I don't know. In my mind, it looks really weird.
I will not go into the generic way to do it. Okay. I'm just going to use this matrix as an example. Okay. And if you do multiplication of two matrices, right? Let's say if X or A matrix times B, right? There's a condition that you could, I mean, for you to do that, for you even to begin doing that, which is the number of columns in A, number of columns in A, has to match the number of rows in B. Number of rows in B. Okay, that's how you can do this multiplication. Okay, now since we're doing M times M, right? And M is a I don't know I don't know if the term is correct, but I'm just going to call it a square matrix. Okay, a square matrix means that it has the same number of rows and columns, right? In this one. So obviously we can do that, right? The rows, number of rows and number of columns match, right? So, oh, we got to do turning that. Okay. See, how do I do? Stop sharing. Okay. what's going on? Okay. So we're doing m times m, right? So I got m up here. M is this. Okay, M is this matrix, right? So to do m times m, we're doing basically this, right? 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 0, 0, 0, 1, 0. This is A, B, C, and D, right? If there's a 1 there, that means there's a connection between node A and node B in here, right? In this first row. A to A, no, we don't count that. A to B, yes. A to C, no. A to D, there's a connection, right? And this times the same matrix. So it's 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 0, and 0, 0, 1, 0. Right? Two exact same matrix. And the way to do multiplication is the result is a matrix of the same dimensions. Okay. So the first spot, AA here, the result is using this row, the first row from the first matrix, to multiply the first column in the second matrix. Okay. When I say row times column, you got to turn it around. Okay. So you got 4 numbers here, right? And 4 numbers here. The way to do this multiplication is use this number, multiply this first number, and the second number, multiply the second number, and the third number, multiply the third number, and the fourth number, multiply the fourth number. And that's why we had talked about this condition earlier, right? For you to be able to do multiplication between 2 matrices, the number of columns in here must equal the number of rows in here, right? That's why you can do this, right? So 0, 0 is 0, right? 1, 0, 0, 0, 0, 1, 0, that's 0, right? That's 4 zeros. You add them together, it's a 0, right? And the next one is this spot, right? So you got 0, 1, 0, 1 times 1, 0, 1, 0. Right? Again, it's 0, right? No question there, right? And now the third spot is 0, 1, 0, 1 and 0, 1, 0, 1. You got 1 plus 1, right? You got 0 plus 1 plus 0 plus 1. So that's why there's 2. Any question there? Okay. So the fourth column, the fourth spot here is 0, 1, 0, 1 times 1, 1, 0, 0. You got a 1 there, right? So there's 1. Right? This is, I mean, if you got a computer, this is a lot easier, but okay. Now the second row here, we use the second row here in the first matrix to do the same multiplication on the second matrix. Okay, so 0, 0, 1, 1 times multiplies 4 zeros. We got a 0, right? And then 0, 0, 1, 1, 1, 0, 1, 0. We got a 1 here. 0, 0, 1, 1, 0, 1, 0, 1. We got a 1 there. 0, 0, 1, 1, 1, 1, 0, 0. We got a 0. Everyone get that? Okay. Yeah, well, just do the same thing here, right? 0, 1, 0, 0, 0. 0, 1, 0, 0, 0, right? 0, 1, 0, 0, 0, 1, 0, 0, got a 1. 0, 1, 0, 0, 0, 1, 0, 0, again, got a 1. Right? 0, 0, 1, 0, 0. 0, 0, 1, 0, we got a 1. Okay, 0, 0, 1, 0, 0, 0, 1, 0, again 0. 0, 0, 0, 0, 1, 0, 0. Right? That's how we do matrix multiplication. Yeah.
So how do you get higher? How do you get the higher paths?
Well,
You have a link, like path of link 2, but how do you get like path of link 3?
we do multiplication again.
So you just multiply that by
You multiply. This is basically m squared, right? This is m times m, and you want to do it again. You just copy this matrix over and do it again.
So is m squared times
Yeah, you can do
m squared times m.
right. You can just do as many times as you want to, right? And then you figure out if there's a path from one node to another. Right? And I think there's usually you have to set a limit to, you don't want to go over 100, for example. That means right? There's no way. I mean, if you have to go more than, because you only have 4 nodes in here, right? In this graph. If you have to go more than 3, you're probably going in a loop there already, right? If there is a connection. Otherwise, there's just no way to reach that point. No, right? Because you only have 4 nodes in here. There are only possible 3 connections from one node to 3 direct connections from one node to all the others, right? And so if you have to do this more than 3 times to figure out if you have I mean, if you did 3 times and then there's still a 0, you pretty much can conclude that there's no path from this node to that node. We're good. So this is basically how you do matrix multiplication in this situation. Let me go back to sharing. Okay. Sorry. Looks like my computer froze up in that. So I can't share my screen to the remote site, but I don't know. You guys have, I guess Connor is the only person on Zoom, so you would have to watch it later. So now the problem. Let's go back to problem 1. So problem 1 is that we have this graph here, right? And the problem is to find cycles in this graph. For the simple one, it's just, you can literally just eyeball it, right? So from first A to B and then back to A, there's a cycle, right? A cycle basically means that from one node to go out and then eventually come back to this node. right? A, B, A, that's one. And that is the same as if you go from B to A and then B, that's the same cycle, right? The same path that are involved. And then from B, B, C, D, B, right? That's a cycle. And also, again, that is equal to the other two. And then also from C to D, I mean, between C to D, there's a bidirectional link. So you can go back and forth there. So that's one problem. That's one type of problem that you will encounter in these in this category of problems. And then in this one is this really would require you to know how to do this matrix multiplication, right? As I just described earlier. So this problem is asking you, given this graph, to figure out different paths of from A to C of length 2 or 4. Right? For length 2, you would need to calculate the m squared. Right? So that means using this matrix, do a multiplication on itself again. That gives us this matrix, right? So A to C, there's 1. So from this matrix, it tells us there's 1, right? Well, one path of length 2. So what that means is that we can actually, this is a path. I mean, this is an edge to itself, right? So A to A, and then over to C. Right? That's the path of length 2 there. And when we need to figure out length of 4, then we need to do m to the power of 4. Okay, to do that, you would just use the m to the power of 2 time itself. Okay, multiply itself. Right? Then you will get to this. And then you can see that this spot says 3. Right? That means we can figure out 3 paths of length 3 from A to C. Right? So you can, right? Because this is a circle, this is a I don't know, self-connecting edge. So you can cycle here multiple times, right? 1, 2, 3, and then go out to C. And you can also do this, and then go to C, and then back to A, and then over to C again, right? So that's how you can get to 3 of those paths of length 4, right? There are 4 edges involved here. So if you want, if they ask you to find paths of length 3, what do? We just use this matrix, multiply this one, right? And then figure out what we get here. So we don't actually need to figure out everything. We just need to find out what's the value in this spot, right? So the value in this spot, we can just say 101 times 101. I mean 111. And then summarization of that is 2, right? So m to the power of 3 will have a 2 in this spot, right? And we can find out, let's say, obviously we can do A, and then C. No, A, C, right? A, C. That's a path of 3, length 3. And then we can also do this part, right? AC, right? That's a path of length 3. That's how we got, we only need to figure out that this spot has a 2 in m to the power of 3, right? And this last problem is we have a graph represented by this adjacency matrix, right? So just imagine you have one A, B, C, and D. Right? Four vertices, 4 nodes. And then we have these 1, 2, 3, 4, 5, 6, 7 edges, right, between these nodes. And you can just write those down, right? We want to, starting from this matrix, we just assume that we have A, B, C, and D, 4 nodes, right? We have 4 vertices. And then we have AB. This is AB, right? And then this is AD. So we have AB, AB connections, and BA, right? And then BD, CA, and then DB, and DC, right? Now, so we got these written down. Now, if we just draw those 4 nodes, right, on the paper, and then draw these lines, right? Because they're directional, right? Because we can just go from AB, we go from AB first, right? Then we go from AD, and then BA. We can draw that direction over there, and eventually we'll reach this solution, right? This graph. That's basically it. That's how this type of problems are. So, any questions? If not, let me see if my, okay, can I share now? Still can't share? Oh. Oh. Okay. Now, since we can't, oh, give me a second. What I want to do is you guys can do one. Nope. Okay, let's do one. Come on. Okay, let's do one problem. No, sorry, did I get it wrong? Oh, this is not. Okay. Wait, this is the short, wait a minute. Why is this different? Uh, okay, yeah, now this is. Okay, let's do these. Two problems here. So the first problem is asking how many ones are in the adjacency matrix for this directed graph. This should be relatively easy. Think about it. Do you need to draw the whole matrix? How many? What you can do with this one is you just count the number of edges, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? Or
Some of them have like more than one.
is it 9? Did I count it right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. 9 edges. And then you count the ones that has two that are two directional, right? There's 1, 2, and 3. Right? So for the two directional ones, you have 2 ones, right? And all the others have 1. So it's 9 plus 3. Any question about that? Right? Because each one is an indication of adjacency, right? From A to E, there's an adjacency. From A to B, there's an adjacent connection, right? And then for the bidirectional ones, there are 2, right? There's one and another one. So basically that's it. You count the number of edges, and then you count the ones that are bidirectional. 1, 2, 3. And that'll be it. Okay, the second one. Yeah. Second one. I'm actually not quite sure. Okay, so let's do it. You can obviously you can do this A, B, and back to A, right? So that's one. So AC, A, B, A. That's C, right? And then obviously you can do A, B, C, A. That's 4. And then you can do A, B, C, A. That's 5. But I mean, because you can still go on, right? So I don't know if you can add. Okay, I guess you're back to the original point. That's just that's it. That's the end of it. Yeah. That's yep. Yeah. Go ahead. Oh, we're done today. Yeah, I guess that's right. Earlier. I was thinking, if you can go from A to B to C, A, and then go out again. But I guess that would be outside of this. Yeah, that's already the end of the cycle, so that's good. All right. Unplug that for me, and get it out. Okay, we're all done today. Yep, from the wall. Yep. This cord is mine. Thank you.我觉得就是你可以再就是说回顾一下这些东西，然后呢，还有就是他们那个 website， 他们 ACSL 的 website， 对，他们那上面有些内容，然后它里头有一些别人讲的课，就是 YouTube 的 video 也可以看一下，对。没事，他没有上过那个 website。嗯哼。